In 1927, a Belgian priest named Georges Lemaître sat down and did something that would have seemed almost absurd to anyone watching. He took Einstein's equations of general relativity, the ones describing how mass and energy curve the fabric of space and time, and he ran them backward. Not as a thought experiment, not as a philosophical exercise. He actually worked through the mathematics, carefully, line by line, and what he found was that if the universe is expanding now, which he believed it was, then at some point in the distant past, everything must have been closer together. Much closer. Unimaginably close. And he published this, quietly, in an obscure Belgian academic journal that almost nobody read. Einstein himself, when he heard about it, reportedly told Lemaître that his mathematics was correct, but his physics was abominable. Which is a remarkable thing to say to someone who had just used your own equations to reach a conclusion you didn't like. That moment, that quiet publication in a journal most physicists would never open, is a good place to start, because the story of the Big Bang didn't happen the way you probably think it did. The name itself is misleading. The popular image, this sudden explosion in the darkness, a single point that detonated and flung matter outward into empty space, is wrong in almost every way a picture can be wrong. And the real story, the one that actually emerges from a century of measurements and arguments and instruments pointed at the sky, is stranger, subtler, and in many ways more satisfying than the version most of us carry around. So settle in, get comfortable, and let's take this slowly. There's a lot of ground to cover, and none of it needs to be rushed. Let's go back to Lemaître for a moment, because he deserves more time than he usually gets. He was ordained as a Catholic priest in 1923, and the easy assumption, the one people still make, is that a priest proposing that the universe had a beginning must have been trying to smuggle Genesis into physics. But that's not what happened. Lemaître was extraordinarily careful to keep his theology and his cosmology separate. He actually objected years later when Pope Pius XII tried to use his work as evidence for creation. Lemaître didn't want that. He wanted the physics to stand on its own, and it did, because the mathematics was airtight. What he had shown was that Einstein's field equations, when applied to a universe filled with matter, naturally produce solutions in which space itself is either expanding or contracting. A static universe, one that just sits there unchanging, turns out to be unstable. It's like balancing a pencil on its tip. Technically possible for an instant, but the slightest nudge sends it one way or the other. Einstein knew this, by the way. He had seen it in his own equations years earlier, and it had bothered him so much that he added an extra term, a fudge factor, to hold everything still. He called it the cosmological constant, and its only job was to provide a kind of repulsive pressure that would exactly counterbalance gravity and keep the universe from moving. It was, in a sense, the mathematical equivalent of propping a door open with a brick. It worked, but only if you set the value just right, and there was no physical reason for it to have that particular value. Lemaître looked at the same equations without the brick and let the door swing. Now here's the thing. Lemaître wasn't working in a vacuum. He had a clue, a real observational clue, that the universe might actually be expanding. A few years earlier, an American astronomer named Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, had been measuring the spectra of what were then called spiral nebulae. These were fuzzy spiral shapes in the sky, and nobody was entirely sure what they were. Some astronomers thought they were gas clouds inside our own galaxy. Others suspected they might be entire galaxies in their own right. vast collections of stars far beyond the Milky Way. Schleifer wasn't trying to settle that debate. He was just measuring how fast these nebulae were moving, using a technique that had been around for decades. The technique is beautifully simple in principle. When a source of light is moving away from you, the wavelengths of that light get stretched out slightly. They shift toward the red end of the spectrum. If it's moving toward you, they compress, shifting toward the blue. It's the same reason a siren sounds higher pitched when an ambulance is coming toward you and lower pitched when it's driving away. With light, you can measure this shift very precisely, because atoms emit light at specific wavelengths, specific colors, and if you know what color a hydrogen atom should produce, and you see that color shifted a little redward, you can calculate exactly how fast the source is receding. Schleifer did this for dozens of spiral nebulae, and what he found was striking. Almost all of them were red-shifted. Almost all of them were moving away. And some of them were moving away very fast, hundreds of kilometers per second. Think about what that means for a moment. If you're standing in a field and you see a dozen birds flying in random directions, some toward you, some away, some sideways, that's just motion. But if you look up and every single bird is flying away from you, something else is going on. That's not random. That's a pattern, and patterns demand explanations. Schleifer presented his results at a meeting of the American Astronomical Society in 1914, and the room actually applauded, which was unusual for that kind of gathering, but nobody quite knew what to do with the finding. It sat there, this odd collection of redshifts, waiting for a framework that could make sense of it. Lemaître provided that framework 13 years later, and then, 2 years after that, Edwin Hubble provided the second piece of the puzzle that made the whole picture click. Hubble's contribution was distance. Schleifer had measured how fast the nebulae were moving, but he couldn't tell how far away they were. Hubble could, or at least he could get close, because he had access to the 100-inch Hooker telescope on Mount Wilson, which was at the time the largest telescope in the world. And he had a method. Inside some of the nearer spiral nebulae, he could pick out individual stars, and among those stars, he found a particular type called Cepheid variables. These are stars that pulse, brightening and dimming in a regular rhythm. And the crucial thing about them is that the period of their pulsation, how long it takes them to go from bright to dim and back again, is directly related to their intrinsic brightness. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. So if you measure the period, you know how bright the star actually is. And if you know how bright it actually is, and you measure how bright it appears to be from where you're standing, the difference tells you how far away it is. The dimmer it looks compared to what it should be, the farther away it must be. This is worth pausing on, because it's one of the most elegant ideas in all of observational astronomy. You're using the star's own behavior as a yardstick. You don't need to send anything out there. You don't need to bounce a signal off it. You just watch it pulse, and the pulse tells you the distance. Henrietta Swan Leavitt had worked out this relationship between period and luminosity back in 1912, studying Cepheids in the small Magellanic Cloud. And it was her work, painstaking and largely uncelebrated during her lifetime, that gave Hubble the tool he needed. What Hubble found, when he combined his distance measurements with Schleifer's redshifts, was a relationship so clean it was almost suspicious. The farther away a galaxy was, the faster it was receding. Twice as far, twice as fast. 3 times as far, 3 times as fast. A straight line on a graph, and that straight line is what we now call Hubble's law, though it would be fairer to call it the Lemaître-Hubble law. And in fact, the International Astronomical Union voted in 2018 to do exactly that. The relationship meant something profound. It meant that the universe is expanding, and not in the way you might picture, not like a bomb going off with galaxies flying outward through space. It meant that space itself is stretching. The distance between galaxies is growing because the fabric they're embedded in is getting larger. And here's where the popular image starts to go wrong, because when people hear the Big Bang, they almost always picture an explosion, a point in the darkness, a detonation, stuff flying outward into a pre-existing emptiness. But that's not what the physics describes. There was no center. There was no edge. There was no darkness for the explosion to happen in, because the darkness, the space itself, is what was expanding. Everywhere was the center. Every point in the universe was, and still is, moving away from every other point, the way dots painted on the surface of a balloon move apart when you inflate it. No dot is the center of the expansion. No dot is at the edge. The surface itself is all there is, and it's all stretching. This is genuinely hard to hold in your head, and it's worth sitting with for a moment. We're so used to thinking of explosions as things that happen in a place, things that have a center you could point to and say, it started there. But the expansion of the universe doesn't work that way. If you could somehow rewind the expansion, running the clock backward the way Lemaître did with his equations, you wouldn't see everything collapsing toward a single point in space. You'd see all of space collapsing, the distances between everything shrinking, the density and temperature rising everywhere uniformly, until the whole universe, all of it, was in an extraordinarily hot, extraordinarily dense state. Not a point floating in emptiness. A state. A condition. The entire universe compressed. Lemaître called this the primeval atom, which is a lovely phrase even if it's not quite right. He imagined a single quantum of enormous energy that fragmented and expanded into everything we see. The details were wrong, as they had to be, because nuclear physics and quantum mechanics were still being worked out in the 1920s, and he didn't have the tools to describe what that early state would actually look like. But the broad stroke was correct. The universe had a hot, dense beginning, and it has been expanding and cooling ever since. Now, the name Big Bang itself came later, and it came from someone who didn't even believe in the idea. Fred Hoyle, a brilliant and cantankerous British astronomer, coined the term in 1949 during a BBC radio broadcast. Hoyle favored a competing model called the steady-state theory, in which the universe has no beginning and no end. It just goes on forever, with new matter continuously created to fill the gaps as space expands. He used the phrase Big Bang dismissively, almost mockingly, to contrast his elegant, eternal universe with what he saw as this crude, messy alternative. And the name stuck, which is one of those small ironies that science produces from time to time. The theory got its most famous label from someone trying to make it sound ridiculous, but Hoyle's steady-state model had a real elegance to it, and for about 15 years it was a genuinely serious competitor. It made clear predictions. It said the universe should look roughly the same at every epoch, that a snapshot of the cosmos 10 billion years ago should be statistically indistinguishable from a snapshot today. The Big Bang model made a different prediction. It said the early universe should have been hotter, denser, and fundamentally different from what we see now. And it made one very specific prediction that would turn out to be decisive, a prediction about light. If the universe really had been that hot and that dense in its earliest moments, then at some point, As it expanded and cooled, it would have become transparent for the first time. Before that moment, the universe would have been an opaque fog of plasma, too hot for atoms to hold together, with photons scattering off free electrons like headlights in thick fog. But once the temperature dropped enough for electrons to combine with nuclei and form stable atoms, the fog would have cleared, and all that light, all those photons that had been bouncing around for hundreds of thousands of years, would have been released all at once, free to travel in straight lines across the universe forever. That light should still be here. It should be everywhere, arriving from every direction, stretched by the expansion of space from its original blazing temperature down to just a few degrees above absolute zero. A faint, uniform glow filling the entire sky. And in 1964, 2 engineers in New Jersey, working with a horn-shaped antenna that had been built for satellite communications, found exactly that. But the way they found it is a story that deserves its own telling, because Arno Penzias and Robert Wilson didn't set out to discover the oldest light in the universe. They set out to eliminate a noise in their instrument that they couldn't explain, and they spent months trying everything they could think of, including climbing inside the antenna and cleaning out the droppings left by a pair of pigeons that had nested there, before they finally accepted that the noise wasn't coming from the antenna at all. It was coming from everywhere. And that's worth sitting with for a moment, because Penzias and Wilson were not cosmologists. They were radio engineers, careful ones, working at Bell Labs in Holmdel, New Jersey, and their problem was straightforward. They had a beautiful instrument, a 20-foot horn reflector antenna, originally designed to pick up signals bounced off the Echo balloon satellite, and they wanted to use it for radio astronomy. But to do precise radio astronomy, you need to know exactly how much noise your instrument is producing on its own, so you can subtract it and be left with only the signal from the sky. And when they pointed the antenna at what should have been empty sky, at patches far from the Milky Way, far from any known radio source, they kept picking up a faint, steady hiss that would not go away. Now, you might be thinking, well, instruments are noisy. Maybe it was just a technical problem. And that's exactly what they thought. They checked everything. They tested every connection, every cable, every joint in the antenna's throat. They accounted for atmospheric interference, for radiation from New York City, for the heat of the antenna structure itself. They even considered the possibility that the signal was coming from nuclear weapons tests, residual radiation lingering in the atmosphere. Nothing fit. The noise was the same strength no matter where they pointed the antenna. It didn't change with the time of day, didn't change with the season, didn't change when they rotated the horn. It was isotropic, the same in every direction, and it corresponded to a temperature of about 3.5 Kelvin, just 3.5 degrees above absolute zero. A tiny, persistent warmth coming from everywhere at once. The pigeon droppings, by the way, were a real chapter in this story. 2 pigeons had taken up residence inside the horn, and Penzias and Wilson trapped them, drove them to a release site about 30 miles away, and cleaned out what Wilson politely described as a white dielectric material coating the inside of the antenna. The pigeons came back. They were trapped again and, this time, dealt with more permanently. The antenna was cleaned again. The noise did not change by any meaningful amount. And here's the thing. While Penzias and Wilson were scrubbing pigeon droppings and checking cable joints less than 40 miles away at Princeton University, a physicist named Robert Dick and his colleagues Jim Peebles, Peter Roll, and David Wilkinson were building their own antenna specifically to look for exactly this signal. Dickey had independently worked out the same prediction that George Gamow and his students, Ralph Alpher and Robert Herman, had published back in the late 1940s, that the cooling remnant of the early universe should be detectable as a faint microwave glow filling the sky. Alpher and Herman had actually estimated its temperature at about 5 Kelvin, which was remarkably close, but the prediction had been largely forgotten. Dickey's group had rediscovered the idea and was racing to detect the signal before anyone else. So when Penzias, still frustrated by the unexplained noise, happened to mention it to a colleague who had recently heard Peebles give a talk about this predicted radiation, the connection was made almost by accident. Dickey's group got a phone call. The story goes that Dickey hung up the phone, turned to his colleagues, and said, "Well, boys, we've been scooped." 2 papers were published side by side in the Astrophysical Journal in 1965. Penzias and Wilson's paper was remarkably understated. It simply reported the excess antenna temperature and noted that it was isotropic and unpolarized. They didn't claim to have found the echo of the Big Bang. The companion paper, by Dickey, Peebles, Roll, and Wilkinson, provided the cosmological interpretation, explaining that this was consistent with the thermal radiation left over from a hot, dense early universe. Together, the 2 papers changed everything about how we understand the beginning. Think about what that measurement actually established. The steady-state theory, Fred Hoyle's elegant idea that the universe looks the same at all times, that new matter continuously appears to fill the gaps as space expands, predicted no such background radiation. In a universe that has always looked roughly the same, there's no reason for a uniform glow at 3 Kelvin to exist. The Big Bang model, or more precisely, the hot, dense early state that Lemaître had first pointed toward, predicted it explicitly. The universe was once opaque. It became transparent, and the light released at that moment should still be traveling. The measurement matched the prediction. The steady-state theory didn't have an answer. Now, Hoyle and his collaborators tried. They proposed that the radiation might come from starlight scattered by tiny iron whiskers, metallic dust grains in intergalactic space that could thermalize the light and produce something resembling a blackbody spectrum. It was clever, but it required very specific assumptions about the dust, and as measurements of the background radiation improved over the following decades, the spectrum turned out to be an almost perfect blackbody curve. And I mean almost perfect. When the COBE satellite, the Cosmic Background Explorer, measured the spectrum in 1990, the data points fell so precisely on the theoretical blackbody curve that when John Mather presented the results at an American Astronomical Society meeting, the audience gave a standing ovation. The error bars were smaller than the thickness of the line on the graph. No known astrophysical process other than thermal equilibrium in a hot, dense early universe could produce a blackbody that clean. The iron whisker model couldn't do it. Nothing in the steady-state framework could do it. So how do we know the temperature of this radiation so precisely? The answer is that a blackbody spectrum has a very specific shape that depends on only one number, the temperature. You measure the intensity of the radiation at many different wavelengths, you fit the curve, and the temperature falls out. COBE measured it at 2.725 Kelvin, plus or minus a tiny fraction. That number, 2.725, is one of the most precisely measured quantities in all of cosmology. And it tells you something remarkable. It tells you the temperature of the universe right now, the average temperature of empty space far from any star or galaxy. That radiation is in the room with you. It's arriving from every direction, passing through the walls, through you. A faint whisper of microwave light that has been traveling for 13.8 billion years, stretched by the expansion of space from a blazing 3000 Kelvin when it was first released down to just under 3 Kelvin now. You can't feel it. You can't see it. But it's here. And a small fraction of the static on an old untuned television, back when televisions had static, was literally this light. The oldest light there is. But Kobe didn't just confirm that the radiation existed and had the right spectrum. It found something else, something that turned out to be just as important, and in some ways even more surprising. The cosmic microwave background was almost perfectly uniform, the same temperature in every direction to an extraordinary degree. But not quite. There were tiny variations, fluctuations of about 1 part in 100,000, slightly warmer in some spots, slightly cooler in others. And those fluctuations, that faint pattern of hot and cold patches across the sky, turned out to be the seeds of everything. Every galaxy, every cluster of galaxies, every vast cosmic web of matter that we see in the universe today grew from those tiny density differences in the early universe. Where the primordial plasma was just slightly denser, gravity had a little more to work with, and over billions of years, that slight excess pulled in more matter, which pulled in more until stars and galaxies formed. Where the plasma was slightly less dense, matter drifted away, and those regions became the great voids between galaxy clusters. So the cosmic microwave background isn't just evidence that the universe was once hot and dense. It's a snapshot, a baby picture of the universe taken about 380,000 years after whatever happened at the very beginning. And this is where we need to be careful, because the phrase Big Bang does something misleading. It makes you think of a moment, a single instant, a detonation. But what the evidence actually supports is a sequence, a series of phases, each with its own physics, its own time scale, and its own set of things we can and cannot measure. The cosmic microwave background tells us about one specific moment in that sequence, the moment the universe became transparent. It tells us almost nothing about what happened before that. And what happened before that is where the story gets genuinely strange. Because the standard Big Bang model, the one that Penzias and Wilson's discovery confirmed, the one that correctly predicted the background radiation and the abundances of the lightest elements, that model has problems. Real, serious, well-documented problems that were recognized within a decade of its triumph. And the first of those problems is one that sounds almost philosophical, but it's actually a hard physics question. It's called the horizon problem, and it goes like this. The cosmic microwave background is the same temperature in every direction to 1 part in 100,000. That means regions of the sky on opposite sides, regions that are now tens of billions of light years apart, somehow ended up at exactly the same temperature. But here's the difficulty. In the standard Big Bang model, those regions were never in contact with each other. Light, the fastest thing there is, had not had enough time since the beginning of the universe to travel from one of those regions to the other. They could not have exchanged energy, could not have reached thermal equilibrium, could not have coordinated their temperatures. And yet they did. It's as if you opened 2 thermoses on opposite sides of a room that had never been in the same building, and the coffee in both was at exactly the same temperature, down to 1,000th of a degree. The second problem is called the flatness problem, and it's about geometry. General relativity tells us that the total energy density of the universe determines its geometry, whether space is curved like the surface of a sphere, curved like a saddle, or flat like a table. Measurements show that the universe is flat, or so close to flat that we can't measure any curvature. But in the standard Big Bang model, flatness is unstable. Even a tiny deviation from perfect flatness in the early universe would have grown enormously over time. For the universe to be as flat as we measure it today, it would have had to start out flat to something like 1 part in 10 to the 60th power. That's a 1 followed by 60 zeros. That's not a natural starting condition. That's a razor balanced on its edge for 13.8 billion years without falling. These weren't minor quibbles. These were fundamental puzzles, and they pointed to something missing in the standard picture. The Big Bang model described what happened after the universe was already expanding and cooling, and it described it beautifully. But it couldn't explain the initial conditions. It couldn't explain why the universe started out so uniform, so flat, so finely tuned. It was like having a perfect recipe for a cake, but no explanation for why the ingredients were already measured out and sitting on the counter. And in 1979, a young physicist at Stanford named Alan Guth was working on a completely different problem, magnetic monopoles, when he stumbled onto an idea that would change everything. Guth wasn't looking for the origin of the universe. He was trying to figure out why we don't find magnetic monopoles. That distinction matters, because some of the most important ideas in physics have come from people who are looking for something else entirely. Magnetic monopoles are hypothetical particles that carry a single magnetic charge, a north without a south, or a south without a north. You've never seen one. Nobody has. Every magnet you've ever held has 2 poles, and if you snap it in half, you get 2 smaller magnets, each with 2 poles. But in the mid-1970s, a class of theories called grand unified theories, which attempted to merge 3 of the 4 fundamental forces into one framework, predicted that the early universe should have produced enormous numbers of these monopoles. Not a few. Enough to dominate the mass of the universe. They should be everywhere. And yet, not a single one had ever been detected. Guth was a postdoc, bouncing between positions, and he'd been working with a colleague named Henry Tye on this monopole problem. The question they were wrestling with was whether the phase transitions in the early universe, the moments when the unified forces split apart as the universe cooled, could somehow suppress the production of monopoles. Think of it like water. Freezing. When water cools past 0 degrees, it undergoes a phase transition. Liquid becomes solid. But sometimes, if conditions are right, water can supercool. It can stay liquid below its freezing point in a metastable state until something triggers it to crystallize. Guth and Tye were exploring whether the early universe could have done something similar, supercooling through a phase transition rather than completing it immediately. And on the night of December 6, 1979, Guth was working through the consequences of this supercooling, and he realized something that went far beyond monopoles. If the universe had been trapped in a false vacuum state, a state that looks like empty space but carries an enormous energy density, then that energy would have driven an exponential expansion of space. Not the steady, decelerating expansion that the standard Big Bang model described. Something radically faster. Space doubling in size, then doubling again, over and over, in an unimaginably brief interval. Guth wrote in his notebook that night, in block letters, "Spectacular realization," and underneath, he wrote the words that would become the name of the idea: inflation. Here's the thing about exponential growth. It's deceptive. If something doubles 60 times, it doesn't end up 60 times bigger. It ends up about a billion times bigger. Guth's calculation suggested that in a sliver of time so short it makes a nanosecond look like an epoch, something like 10 to the minus 36 seconds to 10 to the minus 32 seconds after whatever time 0 means, the universe could have expanded by a factor of at least 10 to the 26th. Some versions of the theory put it much higher. A region smaller than a proton could have been stretched to something larger than the entire observable universe is today. Now, you might be thinking, how does inflating the universe solve the problems we just talked about? Let's go back to the horizon problem, the puzzle of why opposite sides of the sky have the same temperature even though they've never been in causal contact. Inflation solves this beautifully, almost embarrassingly simply. Before inflation, the region that would become our entire observable universe was tiny. Unimaginably tiny. Small enough that every part of it was in contact with every other part. Light had time to cross it. Energy had time to equilibrate. Everything reached the same temperature the way everything reaches the same temperature in any small, well-connected system, through ordinary thermal processes. Then, inflation took that tiny, uniform patch and stretched it to cosmic scales. The uniformity was already there. Inflation just made it big. And the flatness problem dissolves the same way. Think about the surface of a balloon. When the balloon is small, you can see its curvature easily. But inflate it to enormous size, and any small patch of the surface looks flat. If you were an ant standing on a balloon the size of the Earth, you'd swear the surface was flat in every direction. That's what inflation does to the geometry of space. Whatever curvature existed before inflation, the expansion was so extreme that it stretched any curvature to scales far, far larger than what we can observe. Our observable universe is just a tiny patch on an unimaginably vast surface, and on that patch, space looks flat. It has to look flat, regardless of the overall geometry. The fine-tuning goes away. You don't need the universe to start at 1 part in 10 to the 60th. You just need inflation. And the monopoles? They get diluted. If grand unified theories are right and monopoles were produced before inflation, then inflation took whatever monopoles existed and spread them across a volume so vast that the chance of finding even one in our observable universe is essentially zero. The problem isn't that monopoles were never created. It's that they were created, and then the universe expanded so violently that they were scattered beyond any hope of detection. 3 problems, 1 mechanism. That's the kind of economy that makes physicists sit up. But Guth's original version of inflation had a serious flaw, and he knew it. The problem was getting inflation to stop. In his model, the universe was stuck in a false vacuum, like a ball sitting in a shallow dip on a hillside, rather than rolling down to the valley floor. Eventually, the ball has to get out of the dip. In Guth's picture, this happened through a process called bubble nucleation, little regions of space where the phase transition completed, like bubbles forming in supercooled water. These bubbles would expand and collide, and the energy stored in the false vacuum would be released, reheating the universe and producing the hot, dense plasma that the standard Big Bang model described so well. The trouble was that the bubbles didn't merge properly. The space between them was still inflating, still expanding exponentially, so the bubbles could never catch up to each other. You'd end up with a universe full of isolated bubbles, separated by inflating voids, and the collisions between bubble walls would produce wild inhomogeneities, nothing like the smooth, uniform universe we observe. Guth called this the graceful exit problem, which is a wonderfully understated name for a scenario that essentially wrecked his own theory. And this is where the story takes a turn that's worth slowing down for, because it shows how science actually works when it's working well. Guth published his paper in 1981, fully aware of the graceful exit problem, and he said so openly. He laid out the idea, showed what it could solve, and flagged what it couldn't. Within a year, 2 physicists working independently came up with a solution. Andrei Linde in Moscow and, separately, Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania proposed what became known as new inflation, or slow-roll inflation. Instead of the universe being trapped in a sharp dip and tunneling out through bubble formation, they proposed a potential energy landscape that was much flatter, more like a very gentle slope. The field driving inflation, called the inflaton field, would roll slowly down this gentle slope, and inflation would end not through bubble nucleation, but through the field gradually reaching the bottom of the slope everywhere at once, smoothly, uniformly, no bubbles, no collisions, no graceful exit problem. So how do we know any of this actually happened? That's the question that separates a beautiful idea from a scientific theory, and it's worth being honest about what the evidence actually shows. The most powerful evidence comes from the cosmic microwave background, that ancient light we talked about, the one Penzias and Wilson stumbled into. Remember, Kobe showed that the background radiation was almost perfectly uniform, but had tiny fluctuations, about 1 part in 100,000. Inflation doesn't just explain the uniformity, it makes a specific prediction about those fluctuations. Here's how. In quantum mechanics, empty space is never truly empty. It's full of tiny, random fluctuations, virtual particles popping in and out of existence, energy briefly borrowed and returned. Normally, these fluctuations are unimaginably small, operating on scales far below anything we can observe. But during inflation, space was expanding so rapidly that these quantum fluctuations were stretched to macroscopic scales before they had time to disappear. They were frozen in place, imprinted on the fabric of space itself, like wrinkles stretched into a rubber sheet. These stretched quantum fluctuations became the seeds of all structure in the universe. Every galaxy, every cluster of galaxies, every void between them traces back to a quantum fluctuation that was amplified by inflation and then grew under gravity for 13.8 billion years. And inflation makes a very specific prediction about the statistical properties of these fluctuations. It predicts that they should be nearly scale invariant, meaning the fluctuations should have roughly the same amplitude on all scales, with a slight tilt towards stronger fluctuations at larger scales. The technical term for this is a nearly scale invariant power spectrum, and the tilt is parameterized by a number called the spectral index, usually written as n sub s. Inflation predicts this number should be close to 1, but slightly less than 1. Not exactly 1. Slightly less. In 2013, the European Space Agency's Planck satellite, which mapped the cosmic microwave background with extraordinary precision, measured the spectral index at 0.965, plus or minus about 0.4%. That's close to 1, but definitively less than 1, exactly as inflation predicts. And the fluctuations are Gaussian, meaning their statistical distribution follows a bell curve, which is what you'd expect from amplified quantum noise. The agreement between prediction and measurement here is striking. But let's be careful. Inflation is not a single theory. It's a framework, a class of models, and different versions of inflation make different detailed predictions. The data from Planck ruled out some models and favored others, but it didn't single out one unique version. And there's a prediction that inflation makes that hasn't been confirmed yet, one that would be, if detected, perhaps the most profound measurement in all of cosmology. Inflation predicts that the violent expansion should have generated gravitational waves, ripples in the fabric of spacetime itself, at a level that might be detectable as a faint swirling pattern in the polarization of the cosmic microwave background. This pattern is called B-mode polarization, and finding it would be direct evidence that inflation happened and that it operated at energies close to the grand unification scale. In March of 2014, a team using a telescope at the South Pole called BICEP-2 announced that they had detected this signal. The news was enormous. Papers were written, press conferences were held, and for a few months, it seemed like the smoking gun had been found. But then, over the following year, as the Planck team released more detailed maps of galactic dust, it became clear that the BICEP-2 signal could be entirely explained by dust in our own galaxy, tiny grains of material between the stars that emit polarized light in patterns that can mimic the inflationary signal. The detection was retracted. It was a painful episode, but an honest one. The team had done careful work, but the foreground contamination was worse than anyone had expected, and the galaxy's own dust turned out to be a much more complicated foreground than the models at the time had accounted for. And that's worth sitting with for a moment, because the BICEP-2 story is not a story about failure. It's a story about how hard this particular measurement really is. Think about what the team was trying to do. They were looking for a pattern in the polarization of light that has been traveling for over 13 billion years. Light that last scattered off free electrons when the universe was only about 380,000 years old. And the pattern they were hunting for, this B-mode swirl, would have been imprinted even earlier than that, during the first sliver of a second after whatever started everything. The signal, if it's there, is extraordinarily faint. It's buried underneath emission from our own galaxy, underneath the much stronger E-mode polarization pattern that comes from ordinary density fluctuations, underneath instrumental noise, underneath atmospheric interference. Pulling it out is like trying to hear a single whispered syllable in a stadium during a thunderstorm, while someone next to you is playing a trombone that happens to sound a lot like the whisper you're listening for. That trombone is the galactic dust. Dust grains in the Milky Way are not spherical. They're elongated, and they tend to align with the galaxy's magnetic field, and when they emit thermal radiation, that radiation comes out polarized. The polarization pattern from dust can look, at certain frequencies, remarkably similar to the B-mode signal from primordial gravitational waves. Before Planck released its full dust maps in 2015, the BICEP-2 team had to estimate the dust contribution using the best information available, and they underestimated it. Not because they were careless, but because the dust was genuinely worse in their observing patch than the existing data had suggested. When the Planck dust maps came in, the signal that had looked so clean dissolved into foreground contamination. And here's the thing. The retraction didn't end the search. It sharpened it. The BICEP program continued, upgraded to BICEP-3, and then to a broader effort called the BICEP array, each generation adding more detectors and observing at more frequencies, because the way you separate a cosmological signal from galactic dust is by watching the sky at multiple wavelengths simultaneously. Dust has a spectrum. It gets brighter at higher frequencies in a predictable way. The primordial B-mode signal, being imprinted in the microwave background itself, has a different spectral shape. If you observe at enough frequencies, you can in principle peel the dust away and see whether anything is left underneath. So far, nothing definitive has emerged. The current upper limits on the tensor-to-scalar ratio, which is the number that quantifies the strength of primordial gravitational waves relative to the density fluctuations, have been pushed down to about 0.036 by the combined BICEP and Keck array data together with Planck. That's an upper limit, not a detection. It means that if inflationary gravitational waves are there, they're weaker than that. And some models of inflation predict a signal right around that level or just below it, which means the next generation of experiments might be able to see it, or might push the limit down further and start ruling out large families of inflationary models. Either outcome would be enormously valuable. Now, you might be thinking, if we can't detect these gravitational waves yet, and if inflation is really a framework with many possible versions rather than a single clean theory, then how confident should we be that inflation actually happened? That's a fair question, and it's one that cosmologists argue about more than you might expect. The case for inflation rests on several pillars. It solves the horizon problem, the flatness problem, and the monopole problem, all in one stroke. It predicts a nearly scale-invariant spectrum of perturbations, and we see that. It predicts Gaussian fluctuations, and we see those too. It predicts that the universe should be spatially flat to extraordinary precision, and the measurements from Planck are consistent with perfect flatness. That's a strong record, but there are physicists who point out that inflation was designed to solve the first three problems, so the fact that it solves them is not entirely independent confirmation. The real predictive successes are the spectral index and the Gaussianity, and those are genuine, but they're also broadly consistent with other ideas. The unique smoking gun, the one prediction that would be very hard to explain without inflation, is the gravitational wave signal, and we don't have it yet. There are also deeper conceptual worries. One of them is called the measure problem, and it comes from the fact that many versions of inflation, once they start, never really stop. This is the idea of eternal inflation, which emerged from the work of several physicists, including Alexander Vilenkin and André Linde in the 1980s. The basic idea is that if the inflaton field, the field that drives the exponential expansion, has quantum fluctuations, then in some regions of space those fluctuations will kick the field back up to higher energy before it has a chance to roll down and end inflation. In those regions, inflation continues. Meanwhile, in other regions, the field does roll down, inflation ends, and a hot big bang begins, producing a universe like ours. But the regions that keep inflating expand exponentially, so they always dominate the total volume. Inflation, once started, keeps spawning new regions, new pocket universes, in an endless self-reproducing process. This is a strange picture. It means that our observable universe, everything we can see out to the cosmic microwave background and beyond, might be just one pocket in an incomprehensibly vast structure. A multiverse of pocket universes, each with its own local conditions, possibly even its own effective laws of physics if the underlying theory has enough flexibility. And this is where some cosmologists get uncomfortable, because if inflation produces an infinite number of pocket universes with varying properties, then almost any observation is compatible with the theory somewhere. The theory becomes very hard to test, and a theory that can accommodate anything predicts nothing. Let's be clear about the status of this. Eternal inflation is not a fringe idea. It follows naturally from the same physics that makes inflation work in the first place, and many of the physicists who developed inflation take it seriously. But it is also not established. It's a theoretical consequence of certain models, and we have no observational evidence for other pocket universes and no clear way to get any. The multiverse, as it appears in this context, is not a discovery. It's an implication of a framework, and whether that implication is a feature or a problem depends on who you ask. Paul Steinhardt, one of the physicists who helped develop the new inflation model in the early 1980s, the one that solved Guth's graceful exit problem, has become one of inflation's most prominent critics. His argument is precisely this. He says that inflation started as a theory that made the universe's properties seem inevitable, that explained why the universe had to be flat and uniform, and it has evolved into a framework where almost anything goes, where the properties we observe are just the local accident of our particular pocket. He sees that as a loss, not a gain, and he's not alone. Roger Penrose has raised similar concerns, pointing out that the initial conditions required to start inflation may themselves need explaining, which means inflation might not solve the fine-tuning problem so much as relocate it. On the other side, physicists like Alan Guth and André Linde argue that inflation's predictive successes are real and significant, that the spectral index measurement from Planck is a genuine confirmation of a prediction made decades before the data existed, and that the conceptual worries about eternal inflation and the multiverse, while worth taking seriously, don't undermine the core observational case. The theory predicted a number, the number was measured, and they agreed. That matters. So where does this leave us? It leaves us in the middle of an active scientific conversation, which is exactly where you'd expect to be with a theory that's only about 40 years old, and that makes predictions at energy scales we can't reach with any particle accelerator on Earth. The energies involved in inflation, if it happened at the grand unification scale, are roughly 1 trillion times higher than anything the Large Hadron Collider can produce. We can't recreate inflation in a laboratory. We can only look for its fingerprints in the oldest light we can see, and in the distribution of galaxies and clusters that grew from the seeds it may have planted. And this brings us to something that often gets lost in the way the Big Bang is presented, which is the role of the cosmic microwave background, not just as a confirmation that the universe was once hot and dense, but as a tool, arguably the most powerful tool in all of observational cosmology. Because the CMB is not just a glow, it's a surface. It's the last surface from which light could scatter freely before the universe became transparent, and the patterns on that surface encode an astonishing amount of information about the universe's contents, its geometry, its age, and its fate. When George Smoot and John Mather's team on COBE detected those tiny temperature fluctuations in 1992, they were seeing the seeds. But COBE's resolution was blurry, about 7 degrees on the sky, which is 14 times the width of the full moon. To really read the information written in those fluctuations, you needed to see them at much finer scales. You needed to measure not just that the fluctuations existed, but how their amplitude varied with their angular size. Because that pattern, that curve of amplitude versus angular scale, is sensitive to almost everything about the universe. The instrument that did this, the one that turned the cosmic microwave background from a confirmation into a precision measurement, was a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, launched in June of 2001 and named after David Wilkinson, one of the Princeton physicists who had been part of the original race to detect the CMB back in 1965. Wilkinson had spent decades working on microwave background measurements and died in September of 2002, just over a year after the satellite that would carry his name reached its observing post at a point called L2, about 1 million miles from Earth on the side away from the Sun. And what WMAP found, when it mapped the sky with 35 times the angular resolution of COBE, was a picture so sharp and so detailed that it changed the way cosmologists talk about their own field. Before WMAP, cosmology was sometimes called the science of 2 numbers, maybe 3. After WMAP, it became a science of 6 numbers known to several decimal places, and that difference matters more than it might sound. Here's what WMAP actually measured. It mapped the temperature of the cosmic microwave background across the entire sky with an angular resolution of about 1/3 of a degree, which is roughly the apparent size of the moon seen from Earth. And when you look at that map, you see the same thing Smoot's team saw with COBE, a nearly uniform glow at 2.725 Kelvin with tiny fluctuations, hot spots and cold spots scattered across the sky. But now those fluctuations were resolved into sharp detail, thousands and thousands of individual patches, and the question was not just whether they existed, but what pattern they formed. Think about it this way. If you took a photograph of the surface of a pond and the ripples on it were blurry, you could tell the water was disturbed. But if the photograph were sharp, you could measure the wavelengths of the ripples. You could see which wavelengths were strongest and which were weakest, and from that, you could work backward to figure out what kind of stone was thrown in, how deep the pond was, even what the water was made of. The cosmic microwave background works the same way, except the pond is the early universe, the ripples are sound waves, and the photograph is a map of the sky in microwave light. And yes, sound waves. That's not a metaphor. In the first few 100,000 years after the universe became hot and dense, before it cooled enough for atoms to form, the matter in the universe was a plasma, a soup of charged particles and photons all coupled together, and that plasma could carry sound. Regions that were slightly denser than average would gravitationally pull in more material, compressing the plasma, and the pressure of the photons trapped inside would push back, and the result was oscillation. Compression, then rarefaction, then compression again. Acoustic oscillations, running through the plasma of the early universe at roughly half the speed of light. Now, different wavelengths of sound started oscillating at different times, and by the moment the universe cooled enough for atoms to form, around 380,000 years in, some of those waves had completed exactly one full compression, some had completed 1.5 cycles, some 2, and so on. The ones that had completed exactly one full compression by that moment were at their maximum density contrast, meaning they produced the strongest hot and cold spots on the sky. The ones that were caught mid-cycle produced weaker contrast. So when you plot the strength of the temperature fluctuations against their angular size, you get a curve with peaks and valleys. The first peak corresponds to the sound wave that had time for exactly one compression. The second peak corresponds to one full compression and one rarefaction. The third peak, 1.5 full cycles, and so on. This curve is called the angular power spectrum of the CMB, and it is one of the most information-dense measurements in all of science. The position of the first peak tells you about the geometry of the universe, whether space is flat or curved, because the angular size of that first peak depends on how far the sound had traveled by recombination, and how that distance projects onto the sky, which depends on the curvature of the space the light crossed to reach us. The relative heights of the odd and even peaks tell you the ratio of ordinary matter to dark matter, because ordinary matter participates in the pressure oscillations while dark matter only provides gravity, so they affect the compression and rarefaction phases differently. The overall envelope of the peaks, how quickly they fall off at smaller scales, tells you about the density of the universe and the rate at which structure was being damped by photons leaking out of the oscillations. WMAP measured that first peak with extraordinary precision and found it sitting at an angular scale of about 1 degree. And that one number, the position of that peak, told cosmologists that the geometry of the universe is flat. Not curved like a sphere, not curved like a saddle, but flat, meaning that parallel lines stay parallel, and the angles of a triangle add up to 180 degrees, at least on the largest scales we can measure. The flatness that inflation had predicted, the flatness that had seemed so unlikely without some mechanism to drive it, was right there in the data. But WMAP did more than confirm flatness. By fitting the full shape of the power spectrum, the positions and heights of the first three peaks and the valleys between them, the WMAP team extracted a set of numbers that described the universe with a precision nobody had managed before. The age of the universe came out to 13.77 billion years, give or take about 40 million. The fraction of the universe made of ordinary matter, the protons and neutrons and electrons that make up stars and planets and you, came out to about 4.6%. The fraction made of dark matter, the stuff that gravitates but does not interact with light, came out to about 23%. And the rest, roughly 72%, was something else entirely. And this is where the story takes a turn that nobody in the 1960s or 70s would have predicted, and that even in the 1980s would have sounded speculative. That remaining 72% appeared to be a form of energy associated with empty space itself, something that acts like a repulsive force on cosmic scales, pushing the expansion of the universe to accelerate rather than slow down. It had been given a name a few years earlier, dark energy, after two teams of astronomers studying distant supernovae had independently found, in 1998, that the expansion of the universe was speeding up. The supernova teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, had set out to measure how much the expansion was decelerating, because everyone expected gravity to be gradually pulling things back together. Instead, the distant supernova were dimmer than they should have been, meaning they were farther away than the decelerating models predicted, meaning the expansion had been accelerating for roughly the last 5 billion years. Now, WMAP didn't discover dark energy. The supernova results came first in 1998, 3 years before WMAP even launched. But what WMAP did was provide completely independent confirmation from a completely different method. The CMB power spectrum, the geometry of space, the total energy budget, all pointed to the same conclusion. The universe is about 5% ordinary matter, about 25% dark matter, and about 70% dark energy. And the fact that two entirely different measurements, one from exploding stars and one from the relic glow of the early universe, converged on the same answer is what gave cosmologists the confidence to call this the concordance model. 6 parameters: ordinary matter density, dark matter density, dark energy density, the age of the universe, the amplitude of the initial fluctuations, and the spectral index of those fluctuations, which is how their strength varies with scale. That spectral index, by the way, is the one we talked about earlier. The number that inflation predicts should be close to 1, but slightly less than 1. WMAP measured it at about 0.96, and later, Planck refined it to 0.965, a nearly scale-invariant spectrum, tilted just slightly toward having more power on large scales than small scales, exactly as the simplest inflation models predicted. So here was the cosmic microwave background, this faint glow left over from when the universe was 380,000 years old, and it was telling us not just that the universe had once been hot and dense, but precisely how hot, precisely how dense, precisely how old, precisely how flat, and precisely what it was made of. And the answers were strange. A universe dominated by two things, dark matter and dark energy, that we cannot see, cannot touch, and do not yet understand. Let's sit with that for a second, because it's worth feeling the weight of it. You are lying here, made of ordinary matter, atoms forged in stars, and that ordinary matter accounts for less than 5% of the total energy content of the universe. Everything you have ever seen, every star, every galaxy, every nebula, in every photograph, all of it together is a minor constituent. The rest is dark in the precise sense that it does not emit or absorb light, and we detect it only through its gravitational effects and its influence on the expansion rate. And here's the thing. We know dark matter is there because of how galaxies rotate, because of how galaxy clusters bend light, because of the way the CMB power spectrum looks, because of the way large-scale structure formed. Multiple independent lines of evidence all require it, but we do not know what it is. Decades of particle physics experiments have searched for dark matter particles directly, trying to catch one interacting with a detector deep underground, and so far none of those experiments has produced a confirmed detection. The leading candidates, particles called WIMPs, weakly interacting massive particles, were for a long time considered the most natural explanation because they fell out of certain extensions of the standard model of particle physics. But the energy ranges where WIMPs were expected to show up have been searched thoroughly, and the signal has not appeared. That does not rule them out entirely. There is still parameter space to explore, but the simple, elegant version of the WIMP hypothesis has been under increasing pressure. Dark energy is even more mysterious. The simplest explanation is that it is the cosmological constant, the same term Einstein added to his equations in 1917 to keep the universe static and then reportedly regretted. In modern language, the cosmological constant represents the energy density of the vacuum itself, the energy of empty space. Quantum field theory actually predicts that the vacuum should have energy, but when you calculate how much, using the methods of quantum field theory, you get a number that is roughly 120 orders of magnitude too large. That is not a small discrepancy. That is the worst prediction in the history of physics, and it remains unresolved. The observed value of the cosmological constant, the one that fits the supernova data and the CMB and the large-scale structure, is not zero, but it is fantastically small compared to what the straightforward calculation gives you. Why it has the value it has, why it is not zero and not enormous, is one of the deepest unsolved problems in fundamental physics. So the concordance model, this 6-parameter description of the universe that emerged from WMAP and was sharpened by Planck, is in one sense a triumph. It fits the data beautifully. The CMB power spectrum, the distribution of galaxies, the abundance of light elements, the expansion history measured by supernovae, all of it hangs together. But in another sense, it is a signpost pointing at our ignorance, because 95% of the universe's contents are things we have named but not explained. The model tells you how much dark matter there is, but not what it is made of. It tells you how much dark energy there is, but not why it exists, or why it has the value it does. And this brings us back to the question that has been running underneath everything. The question of how the Big Bang actually happened, what it means to say it happened, and what we can and cannot claim to know about the very beginning. Because the concordance model, for all its precision, describes the universe from about 1 second after whatever happened at the start. The physics of nucleosynthesis, the formation of hydrogen and helium in the first few minutes, is well tested and well confirmed. The physics of recombination, when atoms formed and the CMB was released at 380,000 years, is solid. Inflation, if it happened, covers a sliver of time unimaginably close to the start. But the actual moment, the thing people picture when they hear the words Big Bang, the instant of infinite density and temperature, that remains beyond the reach of any theory we currently trust. And the reason it remains beyond reach has to do with a collision between two frameworks of physics that, despite a century of effort, have never been reconciled: general relativity and quantum mechanics. Those are the two pillars, and they are both spectacular. General relativity describes gravity as the curvature of spacetime, and it works beautifully for planets, stars, galaxies, the large-scale expansion of the universe itself. Quantum mechanics describes the behavior of matter and energy at the smallest scales, particles, fields, probabilities, and it works beautifully for atoms, for nuclear reactions, for the interactions that hold matter together. Each one has been tested to extraordinary precision. General relativity predicts the bending of light around the sun to a degree that has been confirmed again and again. Quantum electrodynamics, one branch of quantum mechanics, predicts the magnetic moment of the electron to about 10 decimal places, and the measurement agrees. These are not rough approximations. These are among the most precisely confirmed theories in the history of science. And for almost everything we encounter, you only need one of them at a time. If you are calculating the orbit of Mercury, you use general relativity, and you do not worry about quantum effects because they are negligibly small at that scale. If you are calculating how an atom absorbs a photon, you use quantum mechanics, and you do not worry about spacetime curvature because the gravitational field of an atom is absurdly weak. The two theories live in separate rooms, and for nearly every practical purpose, that is fine. But the Big Bang, the actual moment, is the one place where they are forced into the same room. Think about what the Standard Model says if you rewind the expansion. The universe gets denser and hotter. Galaxies merge, stars dissolve, atoms break apart, nuclei break apart. Eventually you reach conditions so extreme that all the matter and energy in the observable universe is compressed into a region smaller than an atom. At that point, you need quantum mechanics because the scale is quantum. But you also need general relativity because the gravitational field is overwhelming. You need both theories simultaneously, and when you try to combine them, the mathematics does not just get difficult, it breaks. The equations produce infinities, not the manageable kind that particle physicists learned to handle through renormalization in the 1940s and 50s, but uncontrollable infinities that cannot be subtracted away. The theory stops giving answers. This is not a minor technical problem. It is a fundamental incompatibility in the way the two frameworks describe reality. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics treats everything else as grainy, discrete, probabilistic. When you try to apply quantum rules to spacetime itself, to ask what gravity does at the Planck scale, which is about 10 to the minus 35 meters, roughly 100 billion times smaller than a proton, the smooth fabric that general relativity relies on starts to foam and fluctuate so violently that the concept of distance itself stops being meaningful. You cannot even define here and there in the usual way. John Wheeler, the physicist who coined the term black hole, called this quantum foam, and he described it as early as the 1950s, but describing it poetically and describing it mathematically are very different things, and nobody has managed the second one. So when someone says, the Big Bang happened, what they usually mean, the picture in their head, is a point of infinite density that exploded outward. And that picture comes from taking general relativity's equations and running them backward until the density goes to infinity, and the curvature of spacetime goes to infinity. That point is called a singularity. But here is the thing. A singularity is not a prediction. It is a confession. It is the theory telling you it is broken down. It is general relativity raising its hand and saying, I cannot describe this. My equations are no longer valid here. You need a better theory. The singularity at the beginning of the standard Big Bang model is not a physical object or event that we should take literally. It is a gap in our knowledge wearing a mathematical disguise. And this is actually one of the most important things to understand about the Big Bang as a whole. The phrase itself, which was coined somewhat dismissively by Fred Hoyle in a BBC radio interview in 1949, suggests a single explosive event, a moment of creation, a starting gun. But the science does not actually describe that. What the science describes, with great confidence and precision, is an early, hot, dense state from which the universe has been expanding and cooling. The further back you go from that state, the more confident the physics becomes at certain stages and the less confident it becomes at others. Nucleosynthesis, the formation of the lightest elements in the first few minutes, is confirmed by the observed abundances of hydrogen, helium, and lithium in the oldest stars. The CMB, released at 380,000 years, is confirmed by the most precisely measured thermal spectrum in nature. These are solid, but the first tiny fraction of a second, the part where inflation may or may not have happened, is less certain. And the actual initial moment, the Planck epoch, the first 10 to the minus 43 seconds, is a complete unknown. We have no tested theory that applies there. This is why the search for a theory of quantum gravity has consumed so much effort for so long. String theory, which emerged in the 1960s and 70s and went through several revolutions in the 80s and 90s, was for decades the leading candidate. The basic idea is that the fundamental constituents of nature are not point particles, but tiny, vibrating strings, and that different vibration modes correspond to different particles, including a particle called the graviton that would carry the gravitational force the way a photon carries the electromagnetic force. String theory naturally incorporates gravity in a quantum framework, which is remarkable, but it requires extra spatial dimensions, 6 or 7 of them beyond the 3 we experience, curled up so small we cannot detect them. And the number of possible ways those dimensions can be curled up is enormous, on the order of 10 to the 500, each one corresponding to a different possible universe with different physical constants. This is the string theory landscape, and it led some physicists, Leonard Susskind among them, to argue that perhaps all of those possibilities are realized somewhere in an eternal multiverse, and the reason our universe has the constants it does is simply that we happen to be in one of the versions compatible with observers. You can hear the echo of the fine-tuning problem we encountered with inflation. The question of why the cosmological constant has the value it does, that 120 order of magnitude discrepancy, might be answered by saying that most of the multiverse has a cosmological constant too large for structure to form, and we necessarily find ourselves in a rare pocket where it is small enough. This is called anthropic reasoning, and it is either a deep insight or a surrender, depending on whom you ask. The trouble is that it is very difficult to see how to test it. Loop quantum gravity takes a different approach entirely. Rather than adding new ingredients like strings and extra dimensions, it tries to apply quantum rules directly to general relativity's own description of space-time. The result is a picture in which space itself is not continuous but made of discrete chunks, tiny quanta of volume and area linked together in a network called a spin foam. In this framework, there is a minimum possible volume, roughly the Planck volume, and you simply cannot squeeze space smaller than that. Which means the singularity at the beginning of the Big Bang might be replaced by something else entirely, a bounce. The universe might not have emerged from a point of infinite density, but instead contracted from a previous phase, reached a minimum size dictated by quantum geometry, and then expanded again. This is sometimes called the Big Bounce, and it is a genuine prediction of loop quantum cosmology, not just a philosophical preference. Martin Boyewald published early work on this in the early 2000s, showing that the singularity is resolved in simplified models. But whether those simplified models capture the full complexity of the real universe is still an open question. And that is the honest situation. We have candidate theories. We have mathematical frameworks that are internally consistent and intellectually beautiful. But we do not have experimental evidence that distinguishes between them. The energies at which quantum gravity effects become important, around the Planck energy, are roughly 1 trillion times higher than anything the Large Hadron Collider can reach. We cannot build an accelerator that probes the Planck scale. It would need to be roughly the size of the galaxy. So the direct route is closed, and physicists have had to look for indirect signatures, subtle imprints that quantum gravity might have left on things we can observe. The CMB is the most promising canvas. If the very early universe went through a quantum gravitational phase, the statistical properties of the tiny temperature fluctuations in the CMB might carry traces of it. Certain models of loop quantum cosmology predict slight modifications to the power spectrum at the largest angular scales, the lowest multipoles, where the data from Planck is noisiest and the cosmic variance is largest. Cosmic variance is a fundamental limitation, not an instrumental one. It means that for the very largest patterns on the sky, there are only a few independent samples available because the sky is only so big. And so the statistical uncertainty can never be reduced below a certain floor, no matter how good your telescope is. It is like trying to determine whether a coin is fair by flipping it only 5 times. You simply do not have enough data to be sure. So the situation is this. The concordance model describes the universe from about 1 second onward with extraordinary precision. Inflation may extend that description back to a tiny fraction of a second after whatever happened at the start. But the start itself, the thing the name Big Bang seems to promise, remains behind a wall that our current physics cannot see past. And the wall is not just observational, it is theoretical. We do not yet have the mathematical language to describe what happens when space-time itself is subject to quantum uncertainty. Now, you might think this is frustrating, and in a way it is. But there is something quietly remarkable about the fact that we know where the wall is. We know exactly which questions we cannot yet answer, and we know what kind of theory would be needed to answer them. That is not nothing. A century ago, nobody even knew the universe was expanding. 50 years ago, the CMB had just been discovered and its spectrum had not been measured precisely. 25 years ago, we did not know the expansion was accelerating. The pace of what has been learned is extraordinary, and the tools that might push the boundary further are already being built or planned. And one of the most interesting frontiers, the one that connects directly to the question of what actually happened at the beginning, involves not the CMB, but something even older, something that would let us see past recombination, past nucleosynthesis, past the first second entirely. It involves gravitational waves, and the particular kind of gravitational wave background that might have been generated in the very first moments of the universe's existence. Not electromagnetic radiation, not light in any form, but ripples in the fabric of space-time itself, propagating outward from processes so energetic and so early that no photon could ever carry their signature to us. Here's why that matters so much. Everything we've talked about so far, the cosmic microwave background, the abundances of hydrogen and helium and deuterium, the large-scale distribution of galaxies, all of it traces back to a universe that was already at least 1 second old. And 1 second sounds impossibly early, but by 1 second, the universe had already cooled enough for protons and neutrons to begin assembling into nuclei. The physics governing that era is nuclear physics, well tested in laboratories, deeply understood. The CMB takes us back further, to about 380,000 years, but its patterns encode information about conditions that existed much earlier, during inflation, and possibly even before. Still, those patterns are filtered through everything that happened between their origin and the moment of recombination. They are shadows on a wall, brilliant and informative shadows, but shadows nonetheless. Gravitational waves, though, are different. They pass through matter almost without interacting. A gravitational wave generated in the first trillionth of a trillionth of a trillionth of a second would travel through the entire subsequent history of the universe, through nucleosynthesis, through the plasma era, through recombination, through the formation of galaxies and stars and planets, and arrive here with its waveform essentially intact. It would be carrying direct information from an epoch that no electromagnetic signal can reach. So how do we know gravitational waves even exist? Well, we've detected them directly since 2015, when the LIGO observatories, 2 enormous L-shaped interferometers in Louisiana and Washington state, picked up the signal of 2 black holes merging about 1.3 billion light-years away. That detection, led by Kip Thorne, Rainer Weiss, and Barry Barish, confirmed a prediction Einstein had made almost exactly a century earlier. And since then, LIGO and its European counterpart Virgo have detected dozens more events: black hole mergers, neutron star collisions, each one a ripple in spacetime that stretched and compressed the 4-kilometer arms of the detector by a distance smaller than 1,000th of the width of a proton. Think about that for a second. The instrument is sensitive enough to measure a change in length that is a tiny fraction of an atomic nucleus across a beam of laser light bouncing back and forth inside a tube 4 kilometers long. The engineering required to achieve that, the vibration isolation, the vacuum systems, the laser stability, is one of the most extraordinary technical accomplishments in the history of science. But LIGO detects gravitational waves from astrophysical events, things happening in the relatively recent universe, merging black holes, colliding neutron stars. These are loud, sharp signals from specific directions. What we're interested in here is something much more subtle, a background hum, a gravitational wave background that would be everywhere at once, coming from all directions with no single source, much like the CMB is a background of electromagnetic radiation filling all of space. The analogy is almost exact. Just as the CMB is a relic of the hot plasma that filled the early universe, a primordial gravitational wave background would be a relic of processes that occurred even earlier, possibly during inflation itself. And this is where it connects back to everything we've been circling around. If inflation really happened, if the universe really did undergo a period of exponential expansion driven by some kind of scalar field, then quantum fluctuations in space-time during that expansion would have been stretched to macroscopic scales, producing gravitational waves across a vast range of frequencies. The amplitude of those waves, their spectrum, their statistical properties, would encode information about the energy scale of inflation, about how quickly it ended, about the specific physics of the inflaton field. It would be, in a very real sense, a recording of the universe's first moments, not a reconstruction from indirect clues, but a direct imprint. Now, you might remember the Bicep 2 episode, the 2014 announcement that turned out to be galactic dust rather than primordial gravitational waves. That was a search for the imprint of these waves on the CMB, specifically the B-mode polarization pattern that gravitational waves would stamp onto the microwave background as they passed through it during recombination. And even though that particular detection didn't hold up, the search continues. Bicep array, the successor to Bicep 2, and the Keck array, is operating right now at the South Pole, accumulating more data, pushing the tensor to scalar ratio lower and lower. The Simons Observatory in Chile's Atacama Desert is coming online with tens of thousands of detectors designed to measure CMB polarization with unprecedented sensitivity. And further out, the Lightbird satellite, a Japanese-led mission with international collaboration, is planned for launch in the late 2020s, and it would map the entire sky's polarization from above the atmosphere, free from the contamination that ground-based telescopes have to fight through. But here's the thing. Even if all of these experiments succeed beautifully, they are still measuring the effect of gravitational waves on the CMB. They are still looking at recombination at 380,000 years and reading the signature that earlier gravitational waves left there. To detect the gravitational waves themselves directly at the frequencies corresponding to the earliest moments, you need a different kind of instrument entirely, and that instrument does not exist yet, but it has been designed, and its construction is underway. It's called LISA, the Laser Interferometer Space Antenna, and it is an ESA-led mission scheduled for launch in the mid-2030s. LISA will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, each one trailing or leading the Earth in its orbit around the Sun. Laser beams will link the 3 spacecraft, and the distances between them will be monitored with extraordinary precision. When a gravitational wave passes through, it will stretch one arm of the triangle and compress another, and LISA will measure that change. The arms are 2.5 million kilometers long, compared to LIGO's 4 kilometers, and that difference in scale means LISA is sensitive to much lower frequency gravitational waves, waves with periods of minutes to hours rather than milliseconds. And those lower frequencies are where some of the most interesting cosmological signals live. LISA won't directly detect the primordial gravitational wave background from inflation, at least not at the amplitudes most models predict. The frequencies are not quite right, and the signal would likely be too faint. But LISA could detect gravitational waves from other early universe processes, phase transitions in the fundamental forces, for instance. Think about what happens when water freezes. The molecules rearrange, energy is released, and the structure of the material changes abruptly. Something analogous may have happened in the early universe as it cooled through critical temperatures. The electroweak phase transition, when the electromagnetic and weak nuclear forces separated from each other about 10 picoseconds after the start, may have been violent enough to generate gravitational waves that LISA could pick up. If it did, those waves would tell us about the physics of that transition, about the Higgs field, and possibly about physics beyond the Standard Model, directly, without needing a particle accelerator powerful enough to recreate those energies. And beyond LISA, there are even more ambitious proposals. The Big Bang Observer, a concept for a follow-on mission, would bridge the frequency gap between LISA and LIGO and might be sensitive enough to detect the inflationary gravitational wave background directly. The Einstein telescope, a proposed underground gravitational wave detector in Europe with arms 10 kilometers long, would push ground-based sensitivity to new limits. The Cosmic Explorer concept in the United States envisions arms 40 kilometers long. These are not science fiction. They have detailed technical designs, cost estimates, site surveys. They represent the next generation of instruments that would push our observational reach back past the 1-second barrier, past nucleosynthesis, past the electroweak transition, potentially all the way to the inflationary epoch or whatever preceded it. And there is another avenue that is even stranger, one that does not involve building anything new at all, but instead involves listening very carefully to pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary regularity, some of them rivaling atomic clocks in their precision. If a gravitational wave passes between us and a pulsar, it changes the arrival time of the pulses by a tiny amount. A single pulsar is not enough, but if you monitor dozens of pulsars spread across the sky for years, you can look for correlated changes in their timing, a pattern that would reveal gravitational waves with periods of years to decades. This is called a pulsar timing array, and in 2023, several collaborations, Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array, announced evidence for exactly this kind of signal. A low-frequency gravitational wave background, humming through the galaxy at periods of years. The source is probably supermassive black hole binaries, pairs of enormous black holes in the cores of merging galaxies, slowly spiraling toward each other. But buried underneath that astrophysical signal, there might be a cosmological component, gravitational waves from the early universe, from inflation or from cosmic strings, or from phase transitions. So the picture that is emerging is this: we are not stuck. We are not staring at a wall with no tools. We are building new kinds of eyes, instruments that see in gravitational waves rather than light. And those instruments are beginning to open a window onto the universe before the first second, before the first atom, before the first nucleus. The wall is still there. The Planck epoch, that first 10 to the negative 43 seconds, where general relativity and quantum mechanics both fail, remains beyond direct observation and possibly beyond any observation we can currently conceive of. But the territory between that wall and the 1-second mark, a territory that was completely inaccessible 20 years ago, is starting to come into view. And what we find there, the gravitational wave spectrum, the signatures of phase transitions, the tensor to scalar ratio, will tell us whether inflation really happened, what drove it, how it ended, and whether the universe before inflation was something we can even meaningfully ask about. And that question, whether there is a meaningful before, is not just a philosophical curiosity. It connects to something concrete, something measurable, something that the next generation of instruments might actually address. Because the question of what came before inflation, or whether before even applies, turns out to depend on what kind of universe you think you're living in. And the answer to that is encoded in numbers we can actually go out and measure. Let's come back to that 6-parameter model one more time. the concordance cosmology that Planck nailed down so precisely. 13.77 billion years old, about 5% ordinary matter, 23% dark matter, 72% dark energy. A spectral index of roughly 0.965. A universe that is spatially flat to within the best precision we can measure. 6 numbers. And from those 6 numbers, you can predict the temperature fluctuations in the cosmic microwave background, the distribution of galaxies across the sky, the ratio of hydrogen to helium to deuterium forged in the first few minutes, and the rate at which the universe is expanding right now. That is an extraordinary achievement. 6 numbers, and the universe clicks into place. But here's the thing. Those 6 numbers are not explanations. They are descriptions. They tell you what the universe looks like. They do not tell you why it looks that way. Why is the spectral index 0.965 and not 1.0? Why is there 5 times more dark matter than ordinary matter? Why is the universe flat? Inflation answers some of these. It explains the flatness. It explains the uniformity. It generates the tiny density fluctuations that grew into galaxies. But inflation itself introduces new parameters: the energy scale of the inflatant field, the shape of its potential, how long it lasted, and those parameters are not yet pinned down by observation. They are constrained, yes. The tensor-to-scalar ratio below 0.036 tells you the energy scale cannot be too high. The spectral index tells you the potential cannot be too steep. But within those constraints, there are many possible versions of inflation, and each one gives you a slightly different prediction for the gravitational wave background, for the precise tilt of the spectrum, for the higher-order statistical properties of the CMB fluctuations. So, what the next generation of instruments is really doing is not just confirming that inflation happened. It is trying to distinguish between versions of inflation. And some of those versions have very different implications for what came before. Think about it this way. In the simplest models of inflation, the inflatant field starts in some high-energy state, rolls slowly down a potential, and the universe expands exponentially during that slow roll. When the field reaches the bottom, inflation ends. The energy converts into particles and radiation, and you get the hot, dense state that we used to call the Big Bang. In that picture, the Big Bang is not the beginning. It is the end of inflation, the moment when the inflationary energy dumps into matter and radiation. The actual beginning, if there is one, is whatever set up the conditions for inflation to start, and that is where things get genuinely uncertain. In eternal inflation, the version that André Linde developed in the 1980s, inflation does not end everywhere at once. It ends in patches, in bubbles, and each bubble becomes a universe with its own properties. But the space between the bubbles keeps inflating, forever, and new bubbles keep forming. In that picture, there is no beginning at all. Inflation is eternal into the past as well as the future, and our observable universe is just one bubble in an infinite, ever-expanding foam. Now, a theorem published in 2003 by Arvind Borde, Alan Guth, and Alexander Vilenkin complicates this. The Borde-Guth-Vilenkin theorem shows that any universe that has been, on average, expanding cannot be eternal into the past. It must have had a beginning of some kind. But what that beginning looks like, whether it is a quantum tunneling event from nothing, as Vilenkin proposed, or a bounce from a prior contracting phase, as loop quantum gravity suggests, or something else entirely, remains an open question. The theorem tells you there must be a boundary. It does not tell you what is on the other side. And this is where the philosophical weight of the whole story settles. Because for most of human history, the question of whether the universe had a beginning was a question for theology and philosophy. It was not a question you could test. And then, in the span of about 70 years, from Lemaître's 1927 paper to the Planck satellite's final data release, it became a question with actual numbers attached to it. We know the observable universe has a finite age. We know the hot, dense state began 13.77 billion years ago. We know that state was preceded by something, almost certainly a period, of rapid expansion. And we know that the rapid expansion itself must have had a beginning, though we do not know what that beginning was, or whether the word beginning even means what we think it means when applied to a regime where time itself may not behave the way it does in our everyday experience. That is where the evidence runs out, not at a wall of ignorance, but at a frontier that is actively being explored, with instruments that are under construction right now. The Simons Observatory in Chile's Atacama Desert is taking data, scanning the microwave sky for the faint curl of B-mode polarization that would reveal primordial gravitational waves. Lightbird, the Japanese space mission, is scheduled for launch in the late 2020s, and it will map the polarization of the entire sky from above the atmosphere, free from the ground-based contamination that tripped up BICEP 2. LISA, the European Space Agency's space-based gravitational wave detector, with its 3 spacecraft flying in formation 2.5 million kilometers apart, is expected to fly in the mid-2030s, and it will be sensitive to gravitational waves from the electroweak phase transition, a signal from roughly 10 to the negative 12 seconds after whatever started everything. And the pulsar timing arrays, Nanograv and the others, will keep refining their measurements of the low-frequency gravitational wave background, teasing apart the astrophysical signal from the cosmological one, looking for the fingerprint of the very early universe in the gentle stretching of space between us and the pulsars. None of these instruments will show us the Planck epoch directly. That first sliver of time, 10 to the negative 43 seconds, where the temperature was so high that gravity itself was a quantum phenomenon, remains beyond anything we can currently probe. To understand that moment, we would need a working theory of quantum gravity, and we do not have one. String theory and loop quantum gravity are both serious attempts, but neither has made a prediction that has been tested and confirmed. They remain, for now, mathematical frameworks, waiting for contact with experiment. But the territory between the Planck epoch and the first second is opening up, and that territory is where the real story of the Big Bang lives, the story of how a featureless, exponentially expanding space became a universe full of structure, full of atoms, full of stars and galaxies and planets, and, on at least one of those planets, people lying in the dark wondering how it all started. So let's sit with where we've come. The Big Bang didn't happen the way you probably first heard about it. It was not an explosion in space. There was no center, no edge, no moment where everything flew outward from a single point into a pre-existing void. What actually happened, as far as the evidence can tell us, is that the universe was once in an extremely hot, extremely dense state, and it has been expanding and cooling ever since. The expansion is not things moving through space. It is space itself stretching, carrying everything with it. The cosmic microwave background, that faint glow arriving from every direction, is the light from the moment the universe first became transparent, about 380,000 years in. And before that, There was almost certainly a period of inflation, an exponential expansion driven by a quantum field, which set up the conditions for everything that followed: the flatness, the uniformity, the tiny density fluctuations that gravity spent billions of years amplifying into galaxies. And right now, while you're lying here, that background radiation is in the room with you. It is everywhere, arriving from every direction, at a temperature of 2.725 Kelvin, stretched by the expansion of space, from the searing glow of a young universe into the faintest whisper of microwave light. About 1% of the static on an old, untuned television was this light. It has been traveling for 13.77 billion years, and it will keep arriving tomorrow and the day after that, a little cooler each time, a little more stretched, but still carrying the pattern of those original fluctuations, the seeds of everything. The neutrinos are here too, passing through you right now, billions of them every second, most of them from the sun, but some from the first few seconds of the universe, a cosmic neutrino background, even older than the microwave one, though we have never detected it directly. And the gravitational waves, if they are there, are passing through as well, stretching and compressing space by amounts so small that no instrument has yet been sensitive enough to catch them. But the instruments are getting better. They are always getting better. And that is maybe the part of this whole story that is easiest to rest on. Not that we have all the answers, because we clearly do not. Not that the Big Bang is a finished theory with every detail filled in, because it is not. But that the universe is not hiding from us. It is leaving evidence everywhere, in the light, in the atoms, in the gravitational waves, in the timing of pulsars, in the ratios of elements, in the pattern of hot and cold spots on the oldest surface we can see. And piece by piece, instrument by instrument, sometimes getting it wrong and having to start over, sometimes spending years scraping pigeon droppings out of an antenna only to realize the noise was the most important signal in the history of science. We keep finding more of it. The not knowing is not a void. It is a frontier, and it is moving, and it has been moving in one direction for a century now, toward more understanding, more detail, more of the actual story. You are part of that story, in the most literal physical sense. The hydrogen in your body was made in the first few minutes. The carbon and oxygen and iron were made in stars that lived and died before the sun was born. You are 13.77 billion years of physics, lying in the dark, listening to the quiet. And the universe is still running, still expanding, still cooling, still carrying the light from its earliest moments across distances that grow a little larger with every passing second. It will keep doing that tonight, whether or not anyone is watching. And that, somehow, is one of the most peaceful things there is.